Alright, so for trigonometric substitution, we're going to use this method to evaluate integrals that more often times look like radicals. They have radicals, and we don't have those factors outside of the radical, so we can send a u du and make it a simple u substitution, the way we have been doing it at least for the last 3 sections. All right, so let's have a look at a problem that you solve in Calc 1. So in Calc 1, when you first learned the integral, you were given this problem. Okay, consider that integral from -1 to +1. That shouldn't be a -1, that should be a +1. And well, but the problem here is we cannot use the u substitution in this case. And that's because if we set u to be 1 minus x squared, so equals 1 minus x squared du equals -2x dx, and well, notice we're missing that factor of x, right? So we have a problem there. But still you were able to solve this problem using a different approach, using a geometric approach in this case, because well, if we consider this expression in the radicand as a y, this means y equals the square root of 1 minus x squared. And if we square both sides, what we get? Y squared equals 1 minus x squared, and this is x squared plus y squared equals to 1. And what is that? X squared plus y squared equals 1. What does that equation represent? It's a unit circle. Well, so keeping in mind that the integral, the information the integral gives us is the area under the curve of the given function within the limits a and b. Well, so ultimately what we're dealing with is to find the area of a circle. Yes, we don't have the tools yet to evaluate this integral by hand and then we can get a value, but at least we know how to find the area of a circle. That's what's the formula to find the area of a circle? Pi r squared, right? However, well, be careful because we don't want the area of the whole circle, because this integral right here only has the positive part of this radical, because again, if we go back and solve for y equals plus minus the square root of 1 minus x squared. So technically we have the plus or minus, which represent the upper semicircle and the lower semicircle. But from the original problem, we only want the upper semicircle. So let's draw that and see what we get. So all we're getting is this from -1 to 1. And that's the area that we want to find. And well, what do we have for the area, which is pi r squared? But in this case, because we're finding the area of only half of the circle, let's just multiply by 1/2. And what's the value of r in this case? So from the center to any point, r equals 1. So all we have to do is plug in 1, and that's a 1/2 pi times 1 squared, which is pi over 2. So that's how you solve this problem in Calc 1 using geometry. And then you also had diagonal lines that gave rise to like triangles or other regions that gave rise to rectangles, and then you computed those problems, but using geometry, not really using the methods of integration. And in fact, you wouldn't have been able to evaluate this integral in Calc 1. But today is the day in which we will know how to do that well. So what do we need for trigonometric substitution? Number one, we need to be aware of most of the trigonometric identities, like the Pythagorean identities. Well, all you need to know is sine squared plus cosine squared. Last time I showed you how to obtain the other two by dividing both sides by sine and by dividing both sides by cos, and you get the other two, right? Squares rather. We need the double angle formula. We will use it more often than not, actually. And it's important to keep those two identities in mind. The half angle formula, which is, again, that's also called the power reduction. Which is something we used last time. All right? We may need it for this as well. And other integration formulas like the integral of secant, the integral of cosecant, those may be really useful. All right? And of course, the method relies on using the Pythagorean theorem, on knowing how the Pythagorean theorem, how it works. Okay, so here's the thing. Something I don't like about pretty much every calculus textbook is that, well, you're given this integral. If it is this form, then use this substitution. So what they do is asking you to memorize substitutions, to memorize formulas. And I mean, although it's okay to memorize, of course there's some stuff that I asked you to memorize. There's some other, like in this case, I'm gonna go in a different direction that actually simplifies a lot of the work, because number one, they're asking you to memorize half a page of information with formulas and diagrams, and that there's a lot of room for making silly mistakes when it comes to science. However, everything can be simplified by just knowing how the Pythagorean theorem works. All right. Also, if you check the textbook, the ebook, or check out the book, the Math Center, you will find out how they take like 7 or 8 steps before actually doing the integration. And the way we're going to do it here is, so we're going to set up the triangle, set up the integral, maybe cancel a couple of terms, go straight to the integration, and save a lot of time. So, okay, so what do we mean by knowing how the Pythagorean theorem works? Well, so another version of the Pythagorean theorem is when we solve for b squared. What do we have when we solve for b squared? So that'll be c squared minus a squared. Okay, what are the differences between these two expressions? What did you notice different? Subtraction. And what about, which one has a subtraction? The bottom one. The other one has a sum. All right? Well, so whenever we have an expression that looks like, okay, if we solve for c, we're going to have the square root of a squared plus b squared. And on the other hand, if we solve for b, we're going to have the form c squared minus a squared. Okay? Well, so what is it that, this is the only thing that we need to understand how it works. So, well, whenever we have a sum of squares, this will represent side and side. Alright? Because positive square plus another positive square, well, that's equal to the hypotenuse squared from the beginning here. But whenever we have this, instead, difference of squares, well, what are we going to have in here? What will C represent? Will C represent the side or the hypotenuse? The hypotenuse. And this will represent the missing side, right? Okay, so, and yes, it has to be in this order, not the missing side minus the hypotenuse, because if we think about the geometric implications, which side is the longest on a right triangle? The hypotenuse. What if we had this reverse? A side which is smaller minus a hypotenuse which is bigger? We get a negative number inside of the radical. Take the square root of a negative number, what's that? imaginary numbers. So this is not calculus of imaginary quantities. Of course, you're going to get that when you get to complex analysis, complex variables. So that's something else. So here we need to make sure that we're dealing with real quantities only. So this is all we need to know. All right. So let's do one example. Let's do the integral we had in the previous page. Well, of course, the u substitution, we already agreed that it's not going to work, right? Because, well, I already did the u, so I'm not going to do it again. So the first thing you want to do is identify what do we have. Do you have a sum of squares or do you have a difference of squares? It's going to be a difference of squares, right? And you might want to rewrite this as a something squared minus something squared. What are those somethings actually? Oh, wait a minute. Nope. That's supposed to be simply in the denominator. So those quantities are going to be, on the one hand, 1 and x. Okay, so we are going to construct a triangle. So because in this case we have difference of squares, the first term, the one that has the positive sign, does that represent the hypotenuse or the side? The hypotenuse. That's the longest side, all right? So this is what we're going to do. We're going to draw a triangle. This acute angle will have the symbol theta for the angle, for the substitution in terms of theta. And then from here, well, you have a couple of options. I mean, of course, number one, that number one will be the hypotenuse. And there's two options for the side. You can put the x on the adjacent to the angle or the opposite. My advice is to have that on the opposite side. And well, all we need to do is find the length of the missing side, which is the adjacent. And I mean, of course, you might want to do the Pythagorean theorem for this, but ultimately you will end up with that radical that we're given in the problem. Okay, only for this time I'm gonna do that. So that's 1 squared equals x squared minus b squared. That's the missing side, so b squared, or plus rather. So that's 1 minus x squared, and b equals the square root of 1 minus x squared. That coincides with what we have for the radical part on the integral. All right. So let me just label with that. So that's the square root of 1 minus x squared. Okay, so we have all the information that we need. So on the one hand, we need a substitution in terms of what we have on our triangle here. Number one, for the radical expression, and then we need also for to find at the x, you know, the differential part of the problem. Well, so on the one hand, okay, let me write two quantities here. So if I write x equals to, x over the square root of 1 minus x squared, all right? Or now let me make this a lot simpler. Never mind. Okay. So I'm gonna have a quotient. I'm gonna write a quotient that involves the radical. Number one, we have radical 1 minus x squared over x versus radical 1 minus x squared over 1. Now the question is, which of those two expressions is simpler than the other one? The first one or the second one? Go with the simplest one. So go with the simplest one. So I'm going to erase this one. I'm going to have a 1 over here. Now, what is the trigonometric function that relates radical over 1? That is adjacent over hypotenuse. Cosine. All right, so we got it. trust me, with what I've just did, I've just saved you about 7 or 8 steps that the book does, the way the book does it. All right? Now, we need something else, of course. So we need to relate the variable itself, x, as either x over 1 or x over 1 over x over the square root of 1 minus x, or which of those two is simpler, x over 1 or x over the radical? X over 1, right? That's the simpler one. So from here, okay, let me clear this this 1 minus x squared equals cosine, and from, okay, over here, so x over 1 equals, and what's the trigonometric function? Sine. All right? Sine. Okay. And this is what we're going to use to find the differential part. So we need to find dx. Well, x over 1 is simply x. And let me rewrite it. But we need to differentiate this one. So dx is sine, the derivative of sine, which is cosine, and then d theta. So we have everything we need. So what I'm going to do is I'm going to replace this radical with cosine, and then I'm going to replace nope. I'm going to replace this dx cosine theta with dx over here. All right, those are the two substitutions that we do. Okay, so let's go back to the integral. So the radical becomes simply cosine, and the dx becomes cosine. Well, actually, yeah, cosine. And well, so let's multiply these two together. That's the integral of cosine squared. And well, from the material we covered last time, well, what can we do about the integral of cosine squared? Can we use substitution directly? Any ideas what to do from here? Maybe we can use an identity.
1 minus sine.
1 minus sine. So the integral of 1 minus, it's plus and cosine 2 theta. So that's the power reduction formula. Okay. So from here, let me split it into two integrals, because this is 1/2. This will be the integral of 1/2 d theta, and plus the integral, or rather, well, the integral of 1/2 cosine 2 theta. Well, the integral of 1/2 d theta is simply 1/2 theta. And over here we're going to have the integral of cosine 2 theta. What's the integral of cosine 2 theta? So sine 2 theta times that 1/2 from the integral, but times the other 1/2 right here, that's going to be 1/4. All right, plus c. And we just finished solving the problem using the integrations by using a trigonometric substitution. Now, so what we just did is do the substitution, solve the problem. We need to undo the substitution. How do we do that? Well, using all the information from the right triangle that we have. But on the one hand, be careful, because number one, oh, this is fine. This 2 theta does not match this theta right there. We need to make sure on our solution we have everything in terms of a single theta, not 2 theta, because we solved the triangle for theta, not for 2 theta. And well, we need to use one of the trigonometric identities, sine 2 theta. Those identities can be found on the first page of this handout. All right, so let's see if you can find which identity can we use.
2 sine theta cosine theta.
2 sine theta cosine theta. So this 1/4, I'm going to leave a space for a minute. It's going to be 1/4 2 sine theta cosine theta plus c. And well, we need an expression for tangent. All right, how are we going to get, for theta? How are we going to get an expression for theta? Well, we're going to take it from here. All right, if we solve for theta for this mini equation, theta equals arc sine x. All right, so on the one hand, let me leave the 1/2 again. So this will be 1/2 arc sine of x, and that's a 2/4, which reduces to 1/2. And well, we need to use the information from our triangle to replace sine and cosine respectively. Well, sine, which is opposite over hypotenuse, that means x over 1, and times cosine, which is adjacent over hypotenuse, and we just got the solution for the original integral in terms of the original variable, which is x. Well, let's just clear these denominators here. So that's a 1/2 arc sine x plus 1/2 x square root of 1 minus x squared plus c. All right, so that's one example. So that's the first example. Zoom everything out so you can see the whole thing. All right. Well, of course, the first example might open a few questions, but of course these questions are going to get clearer as we move on to the next example. So let's keep going with the next example, letter B. Okay, for letter B we have the integral of, well, there's actually a double dx here. There's supposed to be only one, so okay, let me just clear it. So number one, what do we have? Focus only on the radical portion of the integrand. Do we have a sum of squares or do we have a difference of squares? It's a difference of squares. So first of all, I would write it as a, well, let's say this is a equals to 2 and this is u equals to x. Alright, so let's set up the right triangle to perform the substitution. Number one, what does that 2 represent? Will that 2 represent the hypotenuse or will that 2 represent the side, one of the sides? It's the hypotenuse, because that's whenever we have the difference of squares, the positive term represents the hypotenuse, so that's going to be our 2. Yep. And again, you have two options for the variable x, either the opposite to the angle or the adjacent. I usually do the adjacent, but of course you should get the same result if you do it the other way around, except for you will get different results, different answers that will be equivalent, because these are trigonometric functions, these are periodic. Due to identities, we can get different forms, but essentially giving us the same result. So let's see, so the remaining side will be the square root of 4 minus x squared. All right, so in this case we're going to do the usual substitution. So the question is, which of these two is simpler, radical over x or radical over 2? Radical over 2, do we all agree that radical over 2 is simpler than radical over x? So because that's going to leave us with less x's than usual. All right, so okay, so radical 4 minus x squared over 2 equals, which trigonometric function is this one? It's cosine again, right? Cosine theta, but in this case we need to solve for the radical. In the previous example we didn't do because the denominator was 1, so we didn't really spend one step doing that. We're going to do that now. And that's a 2 cosine All right, we need to do another substitution, one for simply x, which will be the one that we will use to find the dx, the differential part of the problem. And again, we have two options, x over radical or x over 2. Which of the two is simpler? X over 2, so let's do that one. So x over 2 equals, which trigonometric function is that? That's sine. And then solve for x equals to sine. Alright, from here we're going to take the differential dx. What's the derivative of 2 sine? 2 cosine d theta. And we have the three elements. In this case, we're going to use three elements to do the substitution, because as opposed to the previous example, we didn't have that factor of x squared in the denominator. So we're going to use this x right here to do a substitution for it. So number one, okay, let's go back to the integral. So that's the integral of number one. I'm going to do the denominator first. So x squared, we have a substitution for x, which is 2 sine theta, quantity squared, times the radical quantity. What did we get for the radical quantity? 2 cosine theta. And in the numerator, the dx, which is 2 cosine theta d theta. And trust me, with all that, with these few steps that we did, we just saved like 8 steps from, in comparison from what the book does. All right, so of course, in this case, these can be reduced, and you might want to do that. So let's reduce 2 cosine with 2 cosine, and that's going to leave us with the following. That's going to leave us with the integral of 2 sine squared theta with the d theta in the numerator. And I've made a mistake on purpose to see if you can catch it. What did I do wrong? Which one?
2.
The 2. Be careful, because this power right here affects both the coefficient and the trig function. So that should have been a 4 right there. All right, let's talk about this integral. So if we had 1 cosine here, we could have set u equals sine, du some sort of cosine, and it would have worked. All right, but we don't have it in this case. Well, so we need to think of something else. And well, how about identities? Well, so we can use the reciprocal identities and write, well, I'm going to take this 1/4 outside. That's cosecant squared theta d theta. And well, the integral of cosecant squared, isn't that negative cotangent? Because the derivative of cotangent is cosecant squared, actually negative cosecant squared. So the integral of positive cosecant will give us the negative cotangent plus c. And we're essentially done. All we need to do is to undo the trigonometric substitution looking at the triangle. Not too many steps, because we didn't get any double angles, so which is great. Actually, this problem was very, very short to that end, which is great. Well, cotangent. So what's SOHCAHTOA for cotangent? Adjacent over opposite. Yes, adjacent over opposite. Well, adjacent, which is the radical, and opposite, which is x. So all we do here is negative 1/4 times adjacent, which is the square root of 4 minus x squared over x plus c. Let's just clear the parentheses. Negative square root of 4 minus x squared over 4x. Final answer. All right. I'm going to give it a few seconds. All right. Let's look at the next exercise on the next page. Letter C, the integral of dx over 9x squared plus 4. All right. What do we have this time? How is this problem different from the previous two that we just did?
The x is number 1.
The x,
Has a coefficient.
it has a coefficient. That's number 1. Anything else? It's a sum of squares, so that means the triangle setup will be slightly different, because in this case, well, let's rewrite this. Well, this is technically a u equals to 3x, because that's the quantity whose squared is that 9x squared. And over here we have an a equals to 4. And both, in this case, represent sides. None of these two represent a hypotenuse, right? Because in this case, we have a sum of squares. Those must represent the lengths of the sides of the triangles. So, let's see. Number 1, let's draw a triangle just the same way that we just did. All right. And, well, label theta to be this acute angle. And of course, again, you have options to label the two sides. But again, my advice is to have the opposite to be the variable one, 3x and 4. And of course, again, if you want to spend a couple of steps you doing the Pythagorean theorem, you should get the square root of 9x squared plus 4.
Isn't it actually 2?
Yeah, that's what I meant, but not what I wrote. Thank you. Yep, so that's a 2. And that's a 2. That's a 2. And let me make this look like a 2 as well. All right. Yep. Thank you.
Wouldn't the hypotenuse be 9x plus 4?
Yes, again. Another thing I meant, but not what I wrote. Thank you. All right. Okay, so let's see. Now that we have this setup, again, we're going to do the usual. Have a rational expression, a quotient that involves the radical. But we have two options. Radical over 2 and radical over 3x. Which of those two are simpler? Radical over 2. So let's set square root of 9x squared plus 4 over 2. And what's the trigonometric function that relates those two quantities? Be careful this time. Because we have hypotenuse over adjacent. 1 over cosine or secant, where the radical 9x squared plus 4 equals to secant theta. So score, we have a substitution for the radical, which is great. All right, now we need to find some x itself, so we can do the dx from there. All right, but in this case, yes, this x right here has a coefficient, but don't worry, that's fine. We'll deal with that. So we have two options, either 3x over 2 or 3x over radical. Which of those two is simpler? 3x over 2. And what's the trigonometric function that relates those two? Tangent this time. Okay, let's solve for x. And in this case, well, x, or rather dx, the derivative, what's the derivative of tangent? And we have everything ready to do the substitution. So let's go back to the original problem, to the original integral. We're going to rewrite this integral in terms of x to 1 in terms of theta. Well, recall for the radical part, we got this 2 secant. And the dx part, what about that dx part?
On the outside,
So 2/3 secant squared theta d theta. All right, so the good thing, a lot of stuff cancels here. In particular, well, 2/3 over 2. Let me write 1/3 outside. The 2's cancel. And secant squared over secant, isn't that just secant? And what's the integral of secant? That's one of those formulas I added on the first page of the handout. ln of secant plus tangent plus c. All right? And we just solved the problem in terms of theta. Let's go back and rewrite this in terms of x's, the original variable. How? Well, observing the right triangle and getting the corresponding quantities, well, in accordance with the SOHCAHTOA. Okay, secant. What's SOHCAHTOA for secant? Opposite over hypotenuse over adjacent. That is the square root of 9x squared plus 4 over 2 plus tangent, which SOHCAHTOA for tangent is over, and the opposite in this case is the 3x, and the adjacent is the 2, so that's simply 3x over 2. We're done. All right, let's see. Well, let me leave it over here for a few more seconds in case you're still working on it. So, would you like to give it a try to letter D?